Okay, let's see here. Yeah, it looks like I forgot to record it too. Oh, I remember now. We talked about the VSEPR theory, the valence shell electron pair repulsion theory, how we determine the shapes of molecules. Was that the one where I showed you the yeah. Oh, okay. Hmm. Let me see. Okay, hold on. I think did we well, I think maybe oh, okay. So after that we had the valence bond theory and we talked about hybridization. I remember now. And we talked about the valence bond theory for ethylene, acetylene, geometric isomerism, molecular orbital theory, bond order, aromatic compounds. Yeah. So basically, the PowerPoint. Basically, we completed that starting from hybridization. Yeah, unfortunately, I forgot to record it. So, but hold on, let me check something here. Let me check something here. Okay. Yeah. Yeah, so that's what we did. Okay, so let me bring up on screen. Well, first let me take roll. Ah. All right, so today is the 28th. Okay, Donnelly is here. Levengood is not here. Miller is here. Neff, Norberg. Oh, I keep doing that. Okay, Bartram is here. Blair, not here. Donnelly is here. Elwell. Levengood is not here. Miller is here. Sheffield is here. Sullivan is not here. And Tillis is here. All right, so let me see who sent a message. Okay, I got you, Mr. Donnelly. All right. So, as I said, if I remember correctly the last time, there's one more PowerPoint that I'm going to I don't think I'll be able to finish all the topics covered, but I'll just go as far into it as possible. And that has to do with states of matter and intermolecular forces. That's what we'll be talking about, and we'll go as far into this as is possible. Oh, by the way, before I forget, did you all see the announcement I posted this morning, right? Right? About the test, final exam being a take-home test, right? Okay, so just thought I should remind you of that. Please, make sure that you you follow all the requirements that I have made about making sure that it's in a PDF format, making sure that you do it in your own handwriting, make sure it's in blue or black ink, make sure you write your name on each page. What else? I think that's pretty much it, right? So make sure that you follow all those. Makes it a lot easier for me to grade. Okay, so let me share my screen. Okay, so states of matter and intermolecular forces is what we'll be looking at today. All right, so let's talk about intermolecular forces. These are basically forces of attraction that exist between molecules, all right? So it's very important that you understand the difference between what we call intermolecular forces and intramolecular forces. Intermolecular forces are the forces that exist between molecules. You have one molecule over here, you have another molecule over here, and there's an attractive force between them, right? Intramolecular forces are those forces that exist within a molecule, all right? So for example, in the case of the water molecule, you have an attractive force between the oxygen atom, which is connected to two hydrogen atoms, right? That's an intramolecular force, right? So it's very important that you understand the difference between the two. And in particular, when it comes to intermolecular forces, these can basically determine a lot of the physical properties that are displayed by these substances. And I'm talking about things like boiling point, melting points, vapor pressure, all that good stuff, which we'll be talking about shortly, all right? Okay, so we'll be talking about intermolecular forces for the most part in this chapter. So let's remind ourselves of the difference between a gas, liquid, and solid in terms of their properties, right? So as far as gases are concerned, we spent a whole chapter on that. And by now we are familiar with the behavior of gas particles. They are very energetic, moving around, bumping into each other occasionally, colliding with the walls of the container, and therefore exerts pressure on the walls of the container. And as stated here, the motion of these particles are mainly translational. What that means is that basically the gas particle moves in straight lines, right? Now, liquids, on the other hand, the molecules are close to each other, more closer to each other compared to the gaseous state. And they do move, but not as energetically as in the case of gas particles. In fact, to be more accurate, the movement of liquid particles is that they slide over each other, right? They're in contact with each other, sliding over each other, but they're not as energetic. And the main reason why is because the forces of attraction between the liquid particles are stronger compared to that in gaseous particles. And again, the motion is mainly translational when it comes to how the particles move. In the case of solids, basically, the particles do not move translationally, first of all, right? In fact, they tend to remain in fixed positions relative to each other. And if they do exhibit any motion whatsoever, it is mainly vibrational, all right? So these properties impart, or these observations, impart properties to the different states, right? In the case of gaseous particles, they tend to flow and they tend to occupy the entire volume of the container that they're in. In the case of liquid substances, they tend to flow like gases, but their volume is fixed. So they do not spread out to if the container is large enough, it does not spread out to occupy the entire volume of the container, even though they do adopt the shape of the container that they're in, which is similar to how gases behave, all right? One thing about liquids compared to gases is that their volume is pretty much fixed, right? Whereas gases, their volume can change rapidly or dramatically. In the case of solids, they have a definite shape, fixed volume, and they don't flow, all right? So that's basically a basic summary of the differences between gases, liquids, and solids. So our discussion here will be focused on liquids and solids because we already spent a whole chapter on gases, right? So let's talk about the process of vaporization. And basically, vaporization is what happens when you have a liquid being converted to a gas, right? And this requires energy, right? And this energy can be measured. In fact, we have what is known as the enthalpy of vaporization, which is the amount of heat that must be absorbed in order to vaporize a amount of liquid at a particular temperature, right? So in the case of going from H2O liquid to H2O gas, the amount of energy needed is 44 kilojoules per mole, all right? So that is the enthalpy of vaporization of water. And different substances will have different values for the enthalpy of vaporization. And of course, based on what we have learned before with respect to energy changes, we know that if the enthalpy change going from liquid to gas is positive, 44 kilojoules per mole, that means going the other direction, going from gas to liquid, would be negative 44 kilojoules per mole, right? And we call that value, or we call that process, I should say, condensation. So going from gas to liquid is condensation, going from liquid to gas is vaporization, all right? So the enthalpy of condensation would be equal to negative the enthalpy of vaporization, basically, all right? So as you can see, as I said before, different substances have different values for the enthalpy of vaporization. So this is just a select collection of different substances and their corresponding enthalpy of vaporization, all right? Okay, so let's talk about another property exhibited by liquids. And we're talking about here what is called the vapor pressure, right? And vapor pressure is basically the pressure that is exerted by the vapor of a liquid in dynamic equilibrium with that liquid at a constant temperature. And this is usually observed in closed systems, as you can see in this example. So let's say you have your liquid. Let's say the liquid is water. It's in this container here, and this is closed in this big jar. It's which is inverted over it, right? So initially, you're going to have some liquid molecules going into the gaseous state, and that will continue until you're going to end up with a situation where some of the molecules that was in the gaseous state will go back to the liquid state. So you're going to have this back and forth until you reach a state of equilibrium where the rate of vaporization and the rate of condensation will be the same. So therefore, as a result, the amount of vapor molecules present above the liquid will be constant, all right? So basically, the pressure exerted by the vapor is what we call the vapor pressure of that particular liquid. And what you'll notice is that there is a relationship between the vapor pressure of a liquid and the temperature, right? As you increase the temperature, the vapor pressure increases, which makes sense if you think about it, because when you're increasing the temperature, you're imparting more energy to the liquid. More molecules will use that energy to move from the liquid state to the gaseous state. The more molecules you have in the vapor state, the greater would be the vapor pressure exerted as a result, all right? So that's basically the relationship between the vapor pressure and the temperature. As the temperature increases, the vapor pressure increases. And tables have been put together for water in particular when it comes to comparing or looking at the relationship between the vapor pressure of water and the temperature. And what you'll notice here, as we said before, as the temperature increases, the vapor pressure increases, right? So that is true for water, and that is true for every substance that exists in a liquid state. As you increase the temperature, the vapor pressure would increase, all right? So this graph here basically is a plot of vapor pressure versus temperature, all right? Now, I don't know exactly what each of these substances, these lines represent, but I'm fairly confident that the blue line here represents how the vapor pressure varies with temperature for water, right? Now, for the other substances, A, B, and C, I don't know what they are, but for D, this is for water, all right? And the reason why I can say that will become clear shortly, all right? So let's talk about the boiling point, right? What's the definition of boiling point? So most persons, when you ask them what's a boiling point, by definition, they'll tell you that it's a temperature at which a liquid boils, which is not exactly the case. It is, as stated here, the temperature at which the vapor pressure of the liquid is equal to the external pressure, right? The boiling point is the temperature at which the vapor pressure is equal to the external pressure. And then we have what is known as a normal boiling point, which is the boiling point when the external pressure is 1 atmosphere, all right? So the normal boiling point of water, for example, is 100 degrees because that is the vapor pressure of water. Well, the 1 atmosphere would be the vapor pressure of water at 100 degrees Celsius, right? So what that means basically is that if you reduce the pressure, then the normal boiling temperature is lowered, all right? And going back to, hold on, let me see here. Okay, let me go back to the previous graph here. So going back to this graph here, the reason why I knew that this here is the curve for water is because, let me get my writing thing here, is because the vapor pressure, well, 1 atmosphere is equal to 760 millimeters mercury. And when you draw a line like this from here to cut the curve right here and then drop the vertical down, it's at 100 degrees, right? So therefore, that's why I knew that this blue line here is basically showing you how the vapor pressure changes with temperature for water, because at 100 degrees Celsius, the vapor pressure is equal to 1 atmosphere. So therefore, this is the boiling point of water at 1 atmosphere, all right? And you can determine the boiling point of water at pretty much any external pressure. So for example, let's say that the external pressure is 600 millimeters mercury. All you have to do is draw a line across, and then when it touches the curve, you drop a vertical line down, and you measure that value. And what would be the answer there? This here, right smack in the middle between 80 and 100 is 90, and this is somewhere between 90 and 100. So I would say this is, I would say this is probably about 95 degrees Celsius, right? So basically, the boiling point of water at when the external pressure is 600 millimeters mercury is about 95 degrees Celsius. So that's basically how you would determine the boiling point of water at different pressures. And you can do the same thing for the other substances represented by the curves A, B, and C, all right? Okay, so that's boiling point. Another term that I need to introduce to you here is what is called the critical temperature, which is the highest temperature at which both the liquid and vapor can coexist in equilibrium as physically distinct states of matter. What that means basically is that beyond that point, you cannot tell the difference between the liquid state and the vapor state, right? Correspondingly, the critical pressure is the vapor pressure at the critical temperature. Now, what I want to introduce to you is this diagram here. It's called a phase diagram, right? It's a plot of pressure versus temperature for a substance, right? And these lines here represents the lines where you have equilibrium between different states. So for example, this line here represents the pressures and temperatures where there's an equilibrium between the solid and the gaseous state. This line here represents various pressures and temperatures where you have an equilibrium between the solid and liquid states. And this line here represents the various pressures and temperatures where you have the equilibrium between the liquid and the gaseous state. Now, the critical temperature represented in this diagram here would be at this point here. If you draw a line down where it cuts the x-axis here, that would be the critical temperature. So I'm going to put here TC here as a critical temperature, and the corresponding critical pressure would be here, PC, all right? Now, beyond that, you're going to get what is known as the supercritical fluid, right? Basically, that's a state where you cannot tell the difference between the liquid state and the gaseous state, all right? And by the way, another thing I need to point out here is this point right here, which is called the triple point. I think I have the definition here on the next slide, but basically, the triple point is where you have the solid, liquid and gaseous state coexisting together at the same time. So you have an equilibrium between those three states at that triple point, all right? Okay, so this is the diagram here, basically showing you pictorially what is happening at the critical point. Basically, at the critical point, or just below the critical point, you can still make the distinction between the solid, or I should say, the vapor and the liquid state. Now, so that's what you have in this tube right here. You have the vapor state here, you have the liquid state here. Once you get above the critical point, you form what is called the supercritical fluid. And if you look at this diagram right here, you'll see clearly you cannot tell the difference between those two states. All right. So that's basically what is happening above the critical point. You basically have a situation where you have a fluid. It's not exactly a liquid or a vapor. It's, you know, basically a state which you cannot tell the difference between those two states. Okay, and different substances, of course, have different values for the critical temperature and critical pressure. And in the case of water, the critical temperature is 647.3 Kelvin, and the critical pressure is 218.3 atmospheres, all right? Okay, now let's look at what happens when you have the states changing. Starting from the solid state, or phase, to be more precise. Basically, in order for you to convert, of course, from a solid to a liquid state, we call that process melting or fusion. And the temperature at which you have that equilibrium between the solid state and the liquid state, we call that the melting point. That requires energy. And the energy required for that is called the enthalpy of fusion, which is the amount of energy required to melt a given amount of solid. And then we have another term here, which is known as sublimation. Sublimation is what happens when you have a solid go straight to the gaseous state without undergoing any, or without going through the liquid state, all right? How many of you are familiar with dry ice? Okay, so you know what dry ice is, right? Dry ice is frozen carbon dioxide. And if you're familiar with it, you know that if I took a piece of dry ice and let's say put it on this table right here, what's going to happen? It's going to shrink. And the reason why it shrinks is because it releases carbon dioxide directly to the gaseous state, right? And eventually it will shrink to basically nothing without leaving any liquid residue on the bench, right? So that's basically what sublimation is all about. So it turns out that we can determine the enthalpy of sublimation by simply adding the enthalpy of fusion plus the enthalpy of vaporization, all right? And this is the equation for it. The enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. And here we have a short table with some substances, including water, which gives you values for the enthalpy of fusion for different substances. As you can see here, water has a value of 6.01 kilojoules per mole. Iron is relatively high, 15.19 kilojoules per mole, and so on and so forth. Okay, so next we're going to talk about heating and cooling curves. Basically, this is a plot of temperature on the y-axis versus time on the x-axis. So if you imagine starting with a substance, let's say solid ice, below the freezing point, we all know what's going to happen when you heat it. The temperature will start to rise, all right? Until you get to the melting point. When it gets to the melting point, what happens is that you're going to have the conversion from the solid state to the liquid state. While that happens, the temperature does not budge, right? The temperature remains at the freezing point, which is 0 degrees. So along this line here, basically what you're having is a solid being converted to the liquid state. So along this line, you're going to have the combination of the solid and the liquid state until you get to this point right here, where all the solid has been converted to liquid. And then as you continue to heat it some more, the temperature is going to rise again, all right? Now, one part that is missing from this here, which I'm going to include here, is that when you get to the boiling point, so let's say the boiling point is right here, which is 100 degrees Celsius for water. So let's say this is 100 degrees Celsius. Then what's going to happen is that you're going to have the curve or the line flattening out like this. So here now you're going to have the liquid and the gaseous state along this line until all the liquid has been converted to gas, and then the temperature is going to rise again So you'll only have here the gas at that point, right? So that's basically what we call the heating curve for, in this case, water, which is basically similar for pretty much any other substance. The numbers will change, of course, but the basic shape would be the same, all right? And of course, if you understand this, then you will understand what happens in reverse. When you cool a substance from the gaseous state all the way down to the solid state below the melting point. So basically, the plot of that curve would basically be the mirror image of what you see here, all right? So that's basically what the heating and cooling curve is all about. Okay, so I talked about the diagram before. This is just basically showing you what I described earlier, the phase diagram, which is a plot of pressure versus temperature. I talked about the triple point here. I talked about the supercritical fluid here. And within these regions is where you have the different states existing, right? So for example, if you have a temperature, let's say the temperature is here. Whoops, that's not a straight line. Let me erase. So let's say you have a temperature. Whoops. Let's say you have a temperature here and a pressure here. I'm just going to label this T1 and this P1. Then the substance will exist as a solid because that's where the intersection, that's a region where those two lines intersect, all right? So that's basically the phase diagram. Now, again, let me say that these lines here represents basically the lines where you have the equilibrium between the different states indicated. So this is the line which represents the equilibrium between the solid and gas state. This is the line which represents the equilibrium between the solid and the liquid state. This is the line where you have the equilibrium between the gas and the liquid state, all right? Okay, so that's basically the phase diagram, and here are different curves. This is called the fusion curve. This is called the sublimation curve, and this is called the vapor pressure curve. Okay, let me, and of course I talked about the critical point beyond which you cannot tell the difference between the solid, between the gaseous and the liquid state. And different substances have some different shapes in terms of the phase diagram. This is for this compound mercury 2 iodide. In this case, you have 2 triple points in this particular case, and that's because you have different forms of mercury iodide in the solid state. You have the alpha form and the beta form here. So, you know, mercury is kind of weird, or mercury 2 iodide is kind of weird when it comes to that. This is the phase diagram for carbon dioxide. This shape here, this part here is kind of weird for carbon dioxide. But again, you have a triple point, you have the critical point, and so on and so forth. This is for water, right? The phase diagram for water. And water is kind of unique because basically for this part here, what you'll find is that as the pressure increases, the melting point decreases, which is unique for water. Most other substances, it's the opposite. Okay, so enough of that. So let's talk about the different types of intermolecular forces that can exist in a substance. And the first one we're going to talk about is what are known as dispersion forces. They're also called London forces, named after Fritz London, who provided a theoretical explanation for this observation. And basically, these forces are as a result of an attraction between an instantaneous dipole and an induced dipole, all right? So what do we mean by that? This applies to molecules, or, well, molecules where they are basically nonpolar, right? So basically what you'll find is that such molecules, the electrons are always moving, right? So at one instant, you might have a separation of charge formed temporarily. We call that an instantaneous dipole. That is what is being represented here. And then when that happens, that basically induces another dipole in an adjacent molecules, and that continues for other molecules. As a result of those instantaneous dipoles, there'll be an attraction between them. And that force of attraction between them is called the London forces, or the instantaneous or dispersion dipoles. So that's basically what is being illustrated here. Here we have the unpolarized molecules. Here we have the instantaneous dipole, and that will basically induce another dipole here. This attraction between the partial plus charge and the partial negative charge will be the force of attraction between them. And that would be called the dispersion forces. So this is what happens in nonpolar molecules like hydrogen, oxygen, iodine, and so on, all right? That is also true when it comes to organic molecules that are hydrocarbons, such as octane and this compound, which is known as isooctane, all right? So hydrocarbons, for the most part, with very few exceptions, are basically nonpolar molecules, right? So therefore, the dispersion forces are the forces responsible for holding these molecules together if they exist in a liquid state or solid state. So in the case of octane, as you can see here, it has a boiling point of 125.7 degrees Celsius. We know this to be a nonpolar molecule. So the explanation for the relatively high boiling point is because of the dispersion forces that exist between molecules of this particular compound. The same is true when it comes to isooctane. Its boiling point is relatively high, 99.2 degrees Celsius. Again, for the same reason as in the case of octane, it has that particular boiling point. And as stated here, because these molecules are large, they are more polarizable. In other words, the separation of charge is greater when you have an instantaneous dipole being formed. So therefore, as a result, the intermolecular forces between them would be stronger, and therefore the boiling points would be relatively high. Then we have what is known as dipole-dipole forces. These are forces that exist between permanent dipoles. So if you think of a molecule like carbon, well, not carbon dioxide, carbon monoxide, let's say, what you'll find is that carbon monoxide is polar, and therefore the forces that will exist between molecules of that type will be dipole-dipole forces, where they line up, such as the negative end of one dipole is attracted to the positive end of another dipole. So that is demonstrated in this picture right here, all right? You can also have a situation where a permanent dipole can induce a dipole in a neighboring molecule, which gives what is known as a dipole-induced dipole force, all right? So that can happen as well. So how do we make predictions as to whether or not, or what type of molecular forces that exist? It says here that dispersion forces, which are always present in molecular compounds, become stronger with increased molar mass and elongation of molecules. So basically what they're saying there is that if the molecule is long, or the longer the molecule, or if it has a heavier molecule in terms of molar mass, then the dispersion forces will be greater or stronger. Now, so what that means is that when you're comparing nonpolar substances, those are the two essential factors that we look at in order to predict, to say which molecule has greater or stronger forces and therefore higher melting or boiling points. Dipole-dipole and induced dipole forces are found in polar substances. The more polar the substance, then the greater the intermolecular forces you expect them to be, all right? So those are basically the guidelines that we use to make predictions as to the type of forces and how great the forces are within particular substances. Then we have a special type of intermolecular forces known as hydrogen bonds. And especially when it comes to biological systems, this is a very important phenomenon. So let's deal with what we understand hydrogen bonds to be. Hydrogen bonds is a basically, well, first, let me say this. The term bond used in this context is a bit of a misnomer because it's not a bond in the same sense as in the case of a covalent bond or an ionic bond, right? So as stated here, a hydrogen bond is an intermolecular force where you have a hydrogen atom which is bonded to a particular nonmetal atom in one molecule, and at the same time it's attracted to a nonmetal atom of a neighboring molecule, right? And the thing about a nonmetal atom is that it must be very electronegative. In other words, the other nonmetal atom must be either nitrogen, oxygen, or fluorine, right? So basically, hydrogen bonding will occur when you have hydrogen bonded to any one of these three atoms, all right? So the way this works is, and I'm going to use this picture right here to demonstrate this. This is using the example of water, right? Here we have the oxygen, right? And here are the two hydrogen atoms. So this is hydrogen and this is hydrogen, right? Now, because oxygen is very electronegative, it's going to attract electrons, the shared electrons, towards itself, right? So this oxygen here will have a partial negative charge, and this hydrogen here will have a partial positive charge, right? So that's the direction of the dipole. Now, because hydrogen has only one electron, right, and that electron is being pulled away from it, right? That means that this oxygen here, the size of its charge here is very large. So let me just put here, very large. It is so large that it's going to attract the negative end of the oxygen, or the negative charge of the oxygen, on a neighboring molecule. So this bond right here, this attractive force right here, is what is known as the hydrogen bond. That is a strong attractive force that exists between the hydrogen of one molecule and the oxygen of another water molecule, all right? So that's a hydrogen bond that exists. And as I said before, this is present not only in the case of oxygen, but also if you have hydrogen bonded to nitrogen or fluorine, all right? So the result of hydrogen bonding is many immense collection of observations. For example, the type of crystal structure that ice forms is as a result of hydrogen bond. And I can't get into all the details, but basically as a result of the hydrogen bonding, there's a certain amount of arrangement that would be adopted when water is frozen to form ice, and therefore you end up with basically, for example, snowflakes having particular designs and so on. Another consequence of hydrogen bonding is the fact that solid water is less dense than water. And the reason why is because as a result of hydrogen bonding, the resulting solid takes up more volume for the same mass. So therefore, what you'll find is that ice would be about, if I remember correctly, 90% less dense than liquid water, if I remember correctly. Hydrogen bonding is also the reason why water has a relatively high boiling point, and also it influences the shape and structures of many biological molecules, such as DNA, RNA, proteins, and so on, all that are essential to life, right? So our very lives are dependent on that feature. Now, what this is showing you here is the alpha helix structure. And what you'll see here, for example, you have this hydrogen bond between this hydrogen, which is bonded to a nitrogen, and the oxygen here. And you have another hydrogen bond here. You have another hydrogen bond here. And that basically is responsible for holding the structure together so that it adopts that alpha helix shape. Another consequence of hydrogen bonding is the formation of what we call dimers, whereas you have one molecule here, in this case acetic acid, associating with another molecule of acetic acid, and you'll notice that you have a hydrogen bond here and a hydrogen bond here, all right? You can also have intramolecular hydrogen bonding, as you can see in this molecule here. The name of this compound here is salicylic acid, which is a precursor to aspirin. And you can see clearly there's a hydrogen bond between the hydrogen here and the oxygen here. Another consequence of hydrogen bonding is what is known as surface tension. Surface tension is basically, as stated here, the amount of energy needed to spread a particular substance along its surface. And what you'll find is that water has an unusually high surface tension. And that's because of the interplay between two types of forces, adhesive forces and cohesive forces. Adhesive forces are basically intermolecular forces between unlike molecules, and cohesive forces are the intermolecular forces between like molecules. And what you're going to find is that the cohesive forces between the water molecules is what is responsible for hydrogen bonding, and also responsible for the surface tension being relatively high. And one of the manifestations of this is the fact that, as you can see in this picture, there are some insects that can travel on water without sinking, primarily because of the skin type property of water due to its high surface tension along the surface. So as you can see, this particular insect can walk on water literally without falling in. Okay, and another consequence of hydrogen bonding is the formation of a U-shaped meniscus in a tube, right? In the case of water, basically you have a meniscus which shapes like this, and that's because the cohesive forces between, or the adhesive force between the water molecules and the glass is greater than that of the cohesive forces within the water itself. And this also is responsible for capillary action. If you have a narrow tube that is placed in water, you leave it to stand for a while, the water will move up into the capillary tube against gravity. And again, that is due to the fact that the adhesive force between the water and the glass surface is greater than that of the cohesive forces. Over here, we have the mercury meniscus in a tube, and you see that the shape is opposite, right? And the reason why is because in the case of mercury, the cohesive forces are greater compared to the adhesive forces. So therefore, the attraction between the mercury atoms within mercury is greater than the attraction between the mercury and the glass of the tubing, all right? And then finally here, we have viscosity, which is a manifestation, another manifestation of intermolecular forces. It states here that viscosity is a measure of a liquid's resistance to flow, and basically the one that are more mobile will flow more easily. Hydrogen bonding and intermolecular forces play a part. So basically, if the forces are greater, then they don't flow as much as if the forces between the molecules are less. All right. Okay, so this is just basically a summary of the different types of intermolecular forces that we have covered. Just to review, when it comes to nonpolar molecules, the type of intermolecular forces will be dispersion, and they typically have extremely low to moderate melting points, and they typically are soluble in nonpolar solvents. Polar molecules, they tend to have dispersion forces, just like in the case of intermolecular forces, but they also have...
He left.
Somebody needs to mute themselves, or I will mute you.
No, Markel is here.
So in the case of polar molecules, not only do you have dispersion forces, as in the case of intermolecular forces, but you also have, or as in the case of nonpolar molecules, I meant to say, you also have dipole-dipole and dipole-induced dipole attractions, right? They tend to have low to moderate melting points, and they're soluble in some polar and some nonpolar solvents. And these are some examples. And then we have hydrogen bonding, which basically only occurs where you have molecules where you have hydrogen bonded to any one of these three atoms, nitrogen, oxygen, or fluorine. And they tend to have low to moderate melting points, and they're soluble in hydrogen bonded or some polar liquids, all right? You know, we have not dealt with network covalent compounds yet, but let me jump to ionic compounds. We have dealt with those before. Typically, cations and anions would be their makeup, and they tend to have high melting points, high boiling points. They tend to be non-conductors of electricity as solids, but when in liquids or when in solution or when molten, they will conduct electricity. And then we have what are known as metallic bonds, which are basically cations that are basically immersed in electrons, and that is basically what happens in all metals, right? They tend to be very hard, high melting points, high boiling points. All the properties that are associated with metals will be due to that type of bonding. Okay, so let me see here. I think I'm going to stop here. Yes, I'm going to stop here as far as this chapter is concerned, because to be perfectly honest, it doesn't make any sense I get into, especially crystal lattices. That's a huge topic which you won't have time to complete. What I would suggest you do is that you read up on basically network covalent solids, allotropes of carbon, and that's it, all right? I'm just going to stop here. And what I'm going to do is give you this assignment to work on now, which is chapter 11. And for those of you out there in Zoom, let me make this public for you right now. Okay, so for you guys out there in Zoom, you can get started on that. I've just published it. Okay, so. There you go. And I can help you out a bit with a couple of these questions. Starting with the first one. It says, predict which substance in each pair will exhibit the higher vapor pressure at a given temperature, and you're to explain your reasoning. All right. So the first pair given is H2O and H2S, right? Water and hydrogen sulfide. So let's look at the structure of water and the structure of hydrogen sulfide. Let me open this up here. Okay, why is this thing not responding? Okay, so H2S or H2O is, and H2S is. So obviously the only difference between them is that you have an oxygen here and a sulfur there, right? So the question is, which one has, what's the question? Which one has a higher vapor pressure? All right. So the one with the higher vapor pressure would be the one with the greater or stronger intermolecular force or forces, right? So you have to ask yourself, which of these two would be would have a stronger intermolecular force between the molecules, right? And if you remember what we just covered, we talked about hydrogen bonding, and we said that hydrogen bonding only occurs with compounds, molecules, where you have hydrogen bonded to one of three elements, three atoms: fluorine, oxygen, nitrogen, right? So in the case of comparing these two, we know that this molecule will exhibit hydrogen bonding. Whereas in this case, you won't have hydrogen bonding, right? So basically, the main forces operating in this particular case would be dispersion forces, because in all molecules, you're going to have dispersion forces. But you're also going to have hydrogen bonding. And you're also going to have dipole-dipole. Right? Because water is polar, so therefore you're going to have dipole-dipole interactions as well. In the case of H2S, you will have dispersion. You will have dipole-dipole. But guess what? You won't have hydrogen bonding. No H bonding. And hydrogen bonding is a particular strong bond. So therefore, the one with the higher vapor pressure would be the water. All right? So that's basically how you deal with that one. All right? Any questions? Any questions about that one? Any questions? All right. Let me clear this. Or is it okay for me to clear this? May I clear this? All right, so the next one, they gave you H2S and H2TE. I forgot what TE stands for. Doesn't matter. Anyway, so in the case of H2S, you have S bonded to H, bonded to H. And in case of H2TE, you have TE bonded to H, bonded to H, right? So again, the question is, which one has a high vapor pressure? Now, in both cases, they both will have dipole-dipole. Same thing over here. They will both also have, what do you call it, dispersion. Same thing over here. But the only difference between them is that you have an S and a T here. Now, when it comes to dispersion and dipole, especially dispersion, one of the things that we learned was that if the larger the molecule, everything else being the same, then the greater would be the dispersion forces, right? So basically, sulfur has a molar mass of 2? I can't see it from here. So basically 32 plus 2 gives you 34 approximately. And in the case of Te, is what? 120, let's call it 128. 128 plus 2 gives you 130. So this has a heavier mass. So therefore, this would be one that has a greater attractive forces, greater intermolecular forces. So therefore, this would have the higher vapor pressure. All right. Okay, any questions about this? Any questions? Any questions? Okay, so let me clear this. The next one they gave you, you're comparing C3H8 to C6H14. These are both hydrocarbons, and hydrocarbons are, for the most part, nonpolar, all right? So they're both nonpolar, so therefore they both have the same dispersion forces. Or same type of dispersion forces. But which one would you expect to have a greater dispersion force as intermolecular forces? For which one would you expect to have a greater intermolecular dispersion force? C6H14, exactly. And the two main reasons, because it's heavier and also the molecule is longer, right? The length of the molecule does influence the polarity or the size of the dispersion forces. So the answer would be C6H14. Okay, what about D? Let me erase this here. In the case of D, they gave you CH2Cl2 and CCl4. Okay, so which of those two would you expect to be, what's the question again? To have a higher vapor pressure? I knew you were going to say that. And you're right. But why? Let me hear your explanation. Very good. So this is nonpolar. And this is polar. Exactly. So as a result, you'd expect this to have a lower vapor pressure, or I should say a higher vapor pressure, my bad, compared to carbon tetrachloride. Okay, the last one, man, the last one could be an organic chemistry question. Anyway, but you should still be able to do this. By the way, how many of you have to do organic chemistry in their future? 1, 2, okay. Yeah, you'll be getting questions like this. CH3, CH2OH compared to CH3OCH3. So you guys are getting a heads up in terms of what you can expect in your future. Okay, so which of these two would you expect to have a higher vapor pressure and why? Which of these two would you expect to have a higher vapor pressure and why? Why? Exactly. Because of hydrogen bonding, which is possible because, as she mentioned, you have the oxygen bonded to the hydrogen, right? So just to be clear, you still have dispersion forces between these two, right? Every molecular compound, dispersion forces always exist, right? So you have dispersion force here, you have dispersion force here. But the difference is, as she said, hydrogen bonding that can exist between the molecules of the first one, which is impossible in the case of the second one, because in the case of the second one, there's no OH bond. So therefore, no H bonding in this case. So therefore, this one would have the higher vapor pressure. All right. Okay, very good. Let me see what's next. Okay, so let's look at number 2. It says, in which of the following substances, let me scroll down here. Let me bring this up on the screen so we can follow together. Okay, so in which of the following substances is hydrogen bonding likely to play an important role in determining physical properties? And it says circle right one. I think there's only one possible answer. So which one of these will exhibit hydrogen bonding? That's basically what the question is coming down to. So which one of these will exhibit hydrogen bonding? Exactly, because a hydrogen bonded to nitrogen, right? Remember the 3 elements that hydrogen must be bonded to: oxygen, nitrogen, or fluorine, all right? So basically the answer is B. All right, so that's that. Okay, now number 3, it says list the substances, and it gives you those 5 substances in order of increasing boiling points. So in other words, it's starting from the lowest to the highest, right? So which of these 3 would you expect to have the, okay, which of these 5 would you expect to have the lowest? Let's start out with the lowest. Let me give you a little hint, which should help you. Let me turn on my writing thing here. The barium chloride is ionic, right? The hydrogen here is nonpolar covalent. The carbon dioxide here is polar covalent. The HF here is polar covalent. And the neon here is nonpolar. There's no bonds here, but it's nonpolar, all right? So that should help you somewhat. So which of these compounds or substances would you expect to have the lowest boiling point? Well, let me give you another hint then. If I was asked this question, the first thing I would look at is, okay, I would expect that the ones with the lowest boiling point would be nonpolar, right? Because the nonpolar only have dispersion forces between them, okay? Polar will have dispersion forces, but also have polar-polar or dipole-dipole forces, right? And then the next in line would be ionic, right? Ionic has the strongest forces existing between the ions, right? Okay, so basically, when looking at which ones would have the lowest, I would focus on the hydrogen, which is nonpolar covalent, and the neon, which is nonpolar. And then I'll have to ask myself the question, between these two, which one would I expect to have the lowest or the weakest dispersion forces? So between the hydrogen and the neon, which would expect to have the weakest dispersion forces? Why do you say that? No. The actual answer is hydrogen, and it has to do with the molar mass. Remember what I said earlier, right? The greater the molar mass, the greater will be the amount of dispersion forces. So therefore, I would start off with hydrogen as being of the lowest in terms of boiling point, and then I would follow that up with the neon, okay? Okay, what would you expect to come after neon in terms of boiling point? You have three other substances remaining. You have carbon monoxide, you have hydrogen fluoride, and you have ionic, all right? So again, let me kind of help you out a bit. With what's remaining, I would say the next in line would be something that's polar covalent, right? And we have two polar covalent substances. We have carbon monoxide and we have hydrogen fluoride. Now, between those two, which you'd expect to have the lower boiling point? Or in other words, which would you expect to have the lower amount of intermolecular forces? Lower? I would say carbon monoxide, because hydrogen fluoride has hydrogen bonded to fluorine. And what could that lead to? That could lead to what? What type of intermolecular force? You just mentioned it. Come on, come on, come on. What did I say about hydrogen bonded to oxygen, nitrogen, or fluorine? What type of intermolecular force will those compounds display? We just talked about it not more than 5 minutes ago. Hydrogen bonding, right? I remember we said that hydrogen bonding is stronger compared to dispersion and compared to polar-polar interactions. So I would put carbon monoxide here, and then hydrogen fluoride would be the next in line. And then, of course, because barium chloride is ionic, that would be the one with the higher or the highest boiling point, right? The key thing you need to remember, or things you need to remember, is that in terms of the strength of intermolecular forces, dispersion forces are the weakest, but they exist in every molecular compound, right? Then the next in line would be polar dipole-dipole interactions, right? And then the next in line would be hydrogen bonding, right? And then after that, you have ionic forces, all right? But remember, dispersion forces exist in every molecular compound, right? It's just that there are other features that come into play when it comes to polar interactions and hydrogen bonding. Okay, so let me clear this, and let me get out of this, and let me scroll down. Okay, it says here, for A, identify the intermolecular force attraction. Oh, okay. Okay, this is my fault. I should have placed these compounds up here, but okay, all right. Basically, what this question is asking is for you to identify the forces of attraction, intermolecular attractions present in the following substances. They're referring to these substances here, right? This one, and this one. All right, so let's deal with that first. Okay, so of these three compounds, let's talk about, well, let me get my writing thing in order here. Okay, so of these, let's deal with CH3, CH3, CH3. What type of forces, whoops, what type of, where's the eraser? Let me do this again. Okay, so for CH3, what type of intermolecular forces would you expect that substance to have? Dispersion, exactly, and that's it. Dispersion forces, right? What about CH3OH? What type of forces would you expect to be present in that substance? Dispersion and hydrogen bond. Okay, very good. What about the next one, which is CH3, CH2OH? What type of forces would you expect to be present in that particular molecule? Dispersion and hydrogen bond again, exactly. Okay, very good. So that answers the A part. Now the B part says, select the substance with the highest boiling point. So of these three substances, which would you expect to have the highest boiling point? Exactly. Why? Because exactly. In fact, I would expect the hydrogen bond effect to be the same. The dispersion force here would be larger because it's a larger molecule compared to the CH3OH, right? So basically the answer is CH3, CH2OH. Larger molecule. Therefore, greater dispersion forces. Okay, so much for that. Okay, let me clear this. And let me scroll down. Okay, so this question is asking for us to calculate, I hope we have enough time to do this one. Calculate the enthalpy change upon converting 1.00 moles of ice at minus 25 degrees to steam at 125 degrees Celsius under constant pressure of 1 atmosphere. It gives you the specific heat of ice, water, and steam, and it gives you the enthalpy of fusion for water and enthalpy of vapor. Okay, so we have everything there that we need to solve this problem. All right, so when answering a question like this, let me go back to my writing. Oh, wait a minute, somebody. Oh, I'm sorry, folks out there in Zoom. I've not been paying attention to your messages. You guys have been trying to answer the questions. So I'll try to pay attention next time. Okay, let me get my writing thing here. Okay, now when it comes to a question like this, where you're taking ice through changes, you're going from solid ice below freezing point all the way up to water or steam at 125 degrees, all right? You have to look at it in parts. So the first part is you start off with H2O, solid, at minus 25 degrees Celsius, right? And then you're going to heat it to form H2O solid at the freezing point, which is 0, I'm going to put 0.0 degrees Celsius, right? So we can calculate the heat change for that. I'm going to call it Q1, right? Then we melt the ice at 0 degrees. So basically what that means is that we're converting H2O solid to H2O liquid at the same temperature, 0.0 degrees Celsius, right? So the heat change for that, I'm going to call that Q2, right? And then we're going to convert H2O liquid to H2O liquid at 100 degrees, right? And I'm going to call the heat change for that Q3. And then now we're going to heat that further from 100 degrees Celsius, H2O liquid to H2O gas. And I'm going to call the heat change for that Q4. And then finally, by the way, H2O gas at 100 degrees Celsius, right? And then finally, H2O gas, we're going to heat it from 100 degrees to 125 degrees, 125 degrees Celsius, right? And I'm going to call the heat change for that Q5, all right? So basically what we need to do is calculate each of these Q values and add them up, and that will give you the total amount of energy required. So to get Q1, that would be equal to, since there's a temperature change, the equation we're going to use for that is one that we met before. Does this look familiar? Does that look familiar? Q is equal to M times C times delta T. In this case, M, we have to find out what M is. They gave us 1 mole of ice, so 1.00 moles. We have to convert that to grams, multiply by 18.02 grams per mole. And then we multiply by the specific heat of Ice, which they gave us as this right here, 2.03 joules per gram Kelvin times the temperature change. What's the temperature change? You're going from 0.0, well, minus 25 to 0.0. So that's 0.0 degrees Celsius minus 25 degrees Celsius. And we work that out, right? So let me see what that gives. So 18.02 times 2.03 times 25. So according to my calculation, rounded out to 3 sig figs, that would be equal to 915. 915, and units would be joules, all right? And by the way, these Kelvin units could be replaced by degrees Celsius. The result will still be the same. So let me just put degrees Celsius here. So that's Q1. And then now for Q2, now in this case, we're melting, right? We're going from solid to liquid. So to calculate the heat change for that, we take the mass, which would be, again, 18.02 grams, because that's 1 mole, multiplied by the enthalpy of fusion, which is this right here. Actually, I didn't need to do that. Hold on 1 minute. I'm sorry. This is my fault. I could just stay with the 1 moles. Because when you do that, when you multiply by this, 6.01 kilojoules per mole, the mole units will cancel out. So you're going to get QB equal to 6.01 kilojoules, all right? So that would be Q2, and I'm running out of space. So let me go up top here. So I'm going to continue up here. So we have just found Q2, so now we can find Q3. Q3 would be going from 0.0 degrees Celsius liquid state to 100 degrees liquid state. So again, we're going to use M times C times delta T. That would be 1.00 mole multiplied by 18.02 grams per mole multiplied by C. Now C in this case is 4.18 joules per gram degree Celsius multiplied by the temperature change, which would be 100.0 degrees Celsius minus 0 degrees Celsius. And let's see what that gives. So that's 18.02 times 4.18 times 100. Okay, so according to my calculations, rounded off to 3 sig figs, this works out to be 7,530 joules. All right. Okay, so that's Q3. All right. Folks, I'm going to need your help. I need you guys to, because I'm going to forget, I need you guys to make a note of these values here because I have to do some erasure because I need more space, right? Q1, Q2, and Q3, because I'm going to ask you for them later on, all right? So what I'm going to do now is erase down here because I need to find Q4 and Q5. Now, in the case of Q4, which is this right here, you're going from liquid water to gaseous water, right? So basically to calculate that, we multiply 1.00 moles times the enthalpy of vaporization, right? So we multiply that by 40.67 kilojoules per mole, and that will give us 40.67 kilojoules, all right? And then in the case of Q5, let me put that down here, that would be equal to, now in this case, you're going from 100 degrees Celsius to 125 degrees Celsius. So again, you're going to use the same equation here, m times c times delta t. M would be equal to 1.00 moles times the molar mass of water, 18.02 grams per mole. And then we're going to add that or multiply that by C, which is 4.18 joules per gram degree Celsius. And then I'm going to multiply that by the change in temperature, which is 125 degrees Celsius minus 100 degrees Celsius. So that part will give us 25 degrees Celsius. So let me see what that gives. 18.02 times 4.18 times 25. So according to my calculation, this works out to be equal to, well, let me do this again. I think I may have made a mistake. Times 4.18 times 25. Let's see what, okay. That was the value. Okay. Now in this case here, I'd have to run this off to 2 sig figs. So that would be 190 joules, right? So that's Q4 and that's Q5, Q4, Q5, all right? So basically what we need to do now is add all of these together. So again, I need to, and I'm going to need your help again because I need to include these values. So I'm just going to erase everything. Okay, so tell me what to write down. Q total is equal to, what's Q1? 915 joules plus, what's Q2? 6.01 kilojoules. Okay, so that means I have to convert this to joules because I'm adding joules and joules together. So I'm going to put 1 kilojoule here, 1,000 joules here, all right? Okay, what's Q3? 7,530 joules. Okay, and then Q4. 40.67 kilojoules. So again, I have to convert this to joules. So I'm going to have 1 kilojoule down here, 1,000 joules above. And then Q5. 190 joules. All right, so basically that's it. So this part here works out to be 6010 joules. This part works out to be so this part here works out to be 4062 joules. All right. So then we just simply add them up. 915 plus 6010 plus 7530 plus 40620 plus 190. And I would have to round this off to the 10th place. So according to my calculations, the answer, final answer, is 55270 joules. Or if you want to express this in kilojoules, 55.27 kilojoules. And that's how that is done. All right. Okay, we have gone beyond the time, so I'm going to leave the rest of this for you to be done by you. When shall this be due? Let's see here. Oh, shucks. Okay, let me see here. So let me set up a Dropbox for this particular assignment. Wait a minute. Okay, so today is the 28th. So I'm going to let it be due on the 30th. Let me just do one quick check of something here. Okay, so I need to do this. Okay, so that's basically where and when you're going to submit your assignment number 11. Let me check something here. So have you guys turned in assignment number 9? No? Whoa, how did I miss that? Nor 10? No? Well, I guess you guys have those to turn in as well. So if you can turn those in as well on that date, that would be very, very good. Let me just check something. Okay. So 9, 10, and 11 will be due on Friday, on what did I say? Friday? Thursday? Okay, so make sure you turn those in and look out for the final exam, which I'm going to publish on, when did I say? Yeah, tomorrow. So look out for that. And I'll be, of course, available during my regular office hours. You have any questions? All right, so that's it for today, folks. Take care. All right. You guys have a test on Thursday, right? Test number 3. I'm getting old. Right, so remember, test number 3 is based on chapters 6, 7, and 8. All right. So make sure that you come prepared for that. I think I'll be available all day tomorrow on Skype from 8 to 11 and 2 to 5, since I have no lab tomorrow. So I'll make myself available on Skype during that time. If you have any questions. What's up?
I don't know if I did that one right.
Well, let's see. So for the first, so
Like, I don't know if those were supposed to be the ones that go together, because all of them have a chlorine, so.
yeah, it shouldn't matter how you do it. For that reason you just mentioned. But let me check your final answer to make sure everything is balanced. You have 4 hydrogens on both sides. You have 4 chlorines on both sides. You have 6 oxygens on both sides. And then as far as the charges are concerned, you have 0 charges on the left and yeah, so that's right. Yeah.
Okay, and then how do I do it when it's like that?
Oh, okay. Now in that case, what you'd have to do is you start off with, oh, shucks. You start off with NO2 going to NO3 minus, and then NO2 going to NO. and then you do the same steps as before.
Okay. I guess that
All right.
works.
Yes, ma'am. Okay.
And then, how do you draw MO diagrams?
Okay, so the MO diagram is based on what we saw in the previous chapter. Where is it? No, hold on. Let me go back this way. Where is it? Oh, wait a minute. Ah, this is what we're talking about. Remember this?
Yeah.
Okay. This is for the elements in the second row, but silicon is in the third row, right? So what that means is that instead of having, no, silicon is right below carbon, right? In group 4. So instead of having sigma 2s here, you're going to have sigma 2p. Well, firstly, for the atomic orbitals, let me use a pencil. Oh, okay. So for the atomic orbitals for silicon, and we're just talking about the valence shell, the electron configuration of silicon is 1s2, 2s2, 2p, 6, then you have 3s2, 3p2. All right. So as far as silicon is concerned, you're going to, and we're only concerned with the valence shell, right? So you're going to have a box here represents the 3s orbital, and then you're going to have 3 boxes represent the 3p orbitals, right? You're going to have 2 electrons here, 1 electron here, 1 electron here. Same thing on this side here. All right. So when these 2 orbitals add together, you're going to have a sigma 3s molecular orbital, bonding orbital, and up here you're going to have a sigma star 3s, right? So that is basically corresponding to what we have here, right? It's just that in the case of carbon, it's 2s, because the second shell is the valence shell. In this case, the third shell is the valence shell, so that's where we have 3s. Now, you'll notice here that in the case of the carbon molecule, you're going to have 2 pi orbitals from the 2p. So here you're going to have 2 pi orbitals two bonding orbitals from the 3p. And then up here, you're going to have, and then just, and this is, you know what? Let me bring this up a bit because I'm going to need a space. So this is one of the 2 pi orbitals. This is another one. All right. And then now, just above it, as you can see here, you're going to have your sigma 3p. Right? Now, I'm just going to redraw this up here. Right? So you're going to have, I'm quite sure you're going to look better when you draw it. Right? So basically, when you have, so these are your 3p orbitals here. So basically, when these are added together, you're going to have that and that, right? And then above it, as you're going to see, going from here to here, you're going to have your pi 3p star antibonding, pi 3p star, and then above it, you're going to have your sigma 3p star antibonding. Right? So basically, you have a total of 2 plus 2 plus 2 plus 2, 8 electrons to distribute among those orbitals. The first two will go here, the second two will go here, and then 5, 6, 7, 8. And that would be basically it as far as the diagram is concerned. Now, it asks for the bond order. Remember, the formula for the bond order is half the number of bonding electrons minus the non-bonding electrons. Right? So, in the case of this molecule, the total number of bonding electrons would be 2, 4, 6. And the total number of non-bonding, I mean, not non-bonding, anti-bonding electrons. Anti-bonding. That's what I meant to say. The total number of anti-bonding electrons would be 2. So that's half of 4, so that's 2. So the bond order would be 2. And it says also tell whether or not the molecule is paramagnetic or diamagnetic. Well, it is paramagnetic if there are any unpaired electrons present, and there's none. So the only other possible answer is diamagnetic, where all the electrons are paired up. And that's it.
Thank you.
All right. Okay. No, final week, no classes.